Welcome to today's Explainer, where we are doing something totally different. We are stepping onto the pitch as the football strategist of the Cambridge examinations. Think about it. Sitting a physics exam is exactly like facing a world-class defense in football. You need formation, you need tactics, and most importantly, you need flawless execution to outplay the question barriers the examiners set up for you. Today, we're taking a seemingly dry physics lab manual on electricity and magnetism and transforming it into our ultimate exam strategy playbook. Whether you're sitting for syllabus 0625, 0651, 0652, 5504, or 9702, the tactics we cover today are absolutely crucial. I'm going to introduce you to two archetypal students. Alex, who overloads his answers with raw physics facts but zero analysis, and Sam, who constantly rushes and completely misses the command word requirements. We'll look at their flawed answers, break down the examiner's red pen marks, and literally make the invisible forces of the universe and the invisible marking criteria of the Cambridge examiners completely visible to you. Let's jump right into the content. Think of this as our strategic playbook for the match. We'll start our first half by plotting invisible magnetic fields and uncovering static electric charges. Then we push into the midfield with flow, current, and resistance before controlling the game's pace through voltage and power. In the second half, we go for the spectacular, merging forces with electromagnetism and finally bending electron beams to secure those top-tier marks. We are taking fundamental principles and turning them into guaranteed points on your paper. Section 1. Plotting invisible magnetic fields, revealing the lines of force. This is where we first meet our two students, Alex and Sam, and see exactly how the Cambridge examiners set up their defensive line to catch them off guard. So, picture a classic 2-mark question asking you to define a magnetic field. The space around a bar magnet might look empty, but it is teeming with structured energy. Remember, unlike poles attract and like poles repel. Now, here's where Alex messes up. Alex writes a massive paragraph about the history of magnets and how the Earth has a magnetic core. He overloads the examiner with facts, but scores 0. Why? Because the command word was define. The only tactic that works here is precision. A magnetic field is specifically a region around a magnet where a force acts. And if the question asks about the lines of force, you must state they are always directed from the North Pole to the South Pole. Boom, 2 points, straight past the defense. Now look at this classic 4-mark practical question. Describe how to plot a magnetic field. This is where Sam always trips up. Sam is a rusher. Sam writes, use a compass and connect the dots. That's it. He entirely misses the command word describe, which requires a sequential, step-by-step methodology. To bypass the examiner's trap, you need our systematic formulation. First, explicitly state, place a plotting compass near the North Pole. Second, mark the positions of both the North and South needle poles. Third, explain the movement. Move the compass so the South needle sits exactly on your previous North mark. Finally, state that you join the points to reveal the continuous magnetic field line. By structuring it like this, you've completely dismantled the assessment objectives and scored full marks. Section 2. Uncovering static electric charges. The transfer of electrons. This is where I want to introduce our ultimate tactical weapon, the Peel framework. Point, evidence, explanation, link. The bedrock of static electricity relies on electron transfer, usually created by friction, like rubbing materials together. If you have two like charges, they repel. If you have unlike charges, one with an excess of electrons and one with a deficit of electrons, they attract. Now, how do top students structure their physics answers for a question on this? They use Peel. Point, state the core physics principle, like unlike charges attract. Evidence, refer back to the specific materials in the question, like a cloth and a polythene strip. Explanation, detail the underlying mechanism, stating that friction causes the transfer of electrons, creating the imbalance. Link, tie it back to the exact scenario the examiner described. If you use Peel, you never leave marks on the table. Let's apply Peel to a real apparatus, the gold leaf electroscope. This is an ingenious device where a delicate gold leaf physically reacts to invisible charges. When you bring a charged strip near the cap, electrons are repelled down into the leaf. Both the rod and leaf become negative, and because like charges repel, the leaf physically rises. Drawing the strip across the edge transfers the charge permanently. Touching the cap with different materials then tests their conductivity. If Sam were answering this, he'd just say, the leaf moves. But with our strategy, you explain the movement of electrons, providing the explanation part of your Peel framework that secures the actual grade. All right, I've got an interactive challenge for you. Imagine the timer is ticking down. What happens when you touch the cap of a charged gold leaf electroscope with your bare hand? Before I give you the perfect Peel answer, I want you to hypothesize. If your body acts as a conductor, where do those trapped electrons go? The answer is that the gold leaf instantly falls because the electroscope is discharged. The excess electrons flow right through your hand, using your body as a conductive path down to the earth. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGC to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Section 3. Flow, Current, and Resistance. Controlling the Invisible River. This marks Act 3 of our playbook, the transformation. We are going to take those red pen marks and turn them into green check marks. We're looking at what happens when electric charges move constantly through a circuit to create current. Here is a beautiful duality. In a series circuit, the current measured by an ammeter is exactly the same at all points. But in a parallel circuit, the current from the cell splits at the junction. The sum of currents in branches equals the total current leaving the junction. Let's do a live rewrite of Alex's typical answer. Alex writes, parallel circuits have different currents everywhere because the wires go different ways. Red pen everywhere. Let's apply our physics success blueprint. We change it to, in a parallel circuit, the total current leaving the junction is conserved. It perfectly equals the sum of the currents traveling through the individual branches. Notice how we use exact terminology like conserved and sum of the currents? That is how you command authority and gain the marks. This equation, Ohm's law, dictates our physical reality. Resistance in ohms is the potential difference, or voltage, divided by the current. Now, Cambridge examiners love to test your understanding of this formula, not just mathematically, but conceptually. They will ask you to explain why a component's resistance changes. If you just write down the formula, you get 1 mark. To get full marks, you need to explain that measuring the voltage across a component and dividing it by the current flowing through it provides the actual resistance, and then link it back to the specific physical properties of the wire in question. Looking at this data table, you can physically prove the formula. A longer, thinner constantan wire, like the 100 centimeter SWG34 wire, chokes the current, dramatically increasing resistance. A short, thick wire offers the lowest resistance. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Section 4. Controlling Voltage and Power, the Potential Divider and Electric Motors. We are now entering Act 4, the interactive workshop. Get ready because I am going to put you on the clock. Challenge 1, data scan. You have a complex physics scenario involving this potential divider equation. By changing just one variable resistor, or a thermistor that reacts to heat, you can divide and control the exact voltage delivered to different parts of a circuit. If R2 is a thermistor, its resistance drops as temperature rises, which changes the ratio and drops voltage V2. I want you to extract the core trend here. As temperature goes up, what happens to the voltage across the thermistor? Time is ticking. The core trend you need to identify for the examiner is the inverse relationship. As heat increases, resistance drops, and therefore the voltage across that specific component decreases. Nailing that trend quickly is how you conquer data analysis questions. Moving to mechanical power, we look at an electric motor lifting a mass. We measure the electrical input power, which is current times voltage. The mechanical lifting power output is mass times gravity times change in height divided by time. Remember, dividing by time is absolutely essential to find the rate of energy transfer. If you forget to divide by time, the examiner's defense tackles you behind the line of scrimmage and you lose the points. Challenge 2. Find the flaw. I'm going to show you a flawed paragraph from Sam answering this exact question about motor efficiency and load size. Sam writes, yes, the efficiency is affected. When you put a heavier mass on the motor, it works harder and uses more power. So the efficiency changes because it is lifting more weight. Can you identify the sentence losing marks? I'll give you a moment. The flaw is his entire lack of scientific justification. Works harder is not a physics term. Let's look at the examiner commentary for that flaw. The examiner wants to see you explain that efficiency is always less than 100% because energy is lost as heat. When you increase the load, the motor draws more current to maintain the lifting force. More current means increased electrical resistance in the internal coils, which generates more heat. Friction in the moving parts also increases. So the ratio of useful mechanical output to electrical input drops. You must explicitly mention electrical heating and mechanical friction to bypass the examiner's defense. Section 5. Electromagnetism and induction. Merging two invisible forces. We are moving into our final tactical drills. This is where we run our speed writing challenge. Challenge 3, speed writing. You have 30 seconds. The question asks you to explain how to create a strong electromagnet and verify its poles. Look at the bullet points. Pass current through a solenoid, use a soft iron core, apply the right-hand grip rule, and know that reversing current reverses poles. Use the Peel paragraph structure in your head right now. Point, wrap a wire coil around a soft iron core. Evidence, passing a current through it induces a magnetic field. Explanation, the soft iron core multiplies the field strength, and gripping the coil with your right hand following the current shows your thumb pointing north. Link, this creates a verifiable electromagnet whose poles can be flipped by reversing the current. If you can synthesize that in 30 seconds, you are operating at an A-star level. Let's look at electromagnetic induction. Moving a magnetic field near a conductor actually induces electricity. The tactic here is understanding rate of change. Moving the magnet quickly cuts through the magnetic lines of force at a higher rate, inducing a large electromotive force, or EMF, and a massive current spike. Moving it slowly induces a very small EMF. This is a classic graphical analysis question. Examiners will show you a spike on a graph and ask you to explain it. Your Peel answer must explicitly link the speed of movement to the rate of cutting magnetic field lines. Section 6. Bending electron beams. The Maltese cross tube. We have reached Act 5, the final system. I am going to lay out the 3 rules that guarantee top marks while we look at this final incredible experiment. Rule 1. Command word decoding. When a question asks you to define cathode rays, you must be precise. These are high-speed beams of electrons accelerated by massive voltage across a vacuum. The vacuum ensures they don't collide with air molecules. The rays are invisible, but they glow when striking a fluorescent screen, proving they travel in straight lines. If the command word is explain why a vacuum is needed, and you just say, so it works better, you fail. You must decode the command word and say, to prevent collisions with air molecules, maintaining the straight trajectory of the electron beam. Rule 2 is the Peel framework application, and Rule 3 is the time management matrix. In this experiment, we fire a cathode ray towards a metal Maltese cross, creating a static shadow. Bringing a North Pole magnet to the cube deflects the shadow. If you get a 6-mark question on this, allocate exactly 1 minute per mark. Do not overwrite like Alex, and do not rush like Sam. Use Peel. Point. The magnetic field exerts a force on the moving electrons. Evidence. The shadow of the cross physically deflects. Explanation. Apply Fleming's left-hand rule. Point your first finger with the magnetic field, your middle finger opposite to electron flow, and your thumb shows the physical force thrusting the shadow. Link. This proves magnetic fields interact with and bend moving electric charges. Flawless execution. If a simple magnet can bend an invisible stream of electrons, imagine what you can achieve when you bend the exam marking scheme to your will. You have the playbook now. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.